Okay, so first thing we got to define what energy is. Energy is a measure of the ability to do work. Okay, so energy is the measure of the ability to do work. That's all it is. All right, and there's different types of energy. There's there's two main types of energy. The first one is called kinetic energy, and this is the energy of motion. So that's what we'll define it as. Okay, it's the, and I abbreviate energy to Nrg. So anytime you see that, that's what it is. Nrg of motion. So something has to be moving in order for it to have kinetic energy. Okay, it is, the kinetic energy is directly proportional. We like to use a fishy to denote what proportional is. Proportional to mass and velocity. Okay, so the symbol for kinetic energy, we like to give it a big capital K and a capital E, KE. The unit, it's the ability to do work, so it has the same units as work. Okay, so the unit is a joule. Okay, and the formula, KE equals mv squared over 2. Some people like to call it 1/2 mv squared, and this is where m is the mass and v is the velocity. mv squared over 2. Some people like to call it 1/2 mv squared. I don't like fractions, so I just do mv squared over 2. Okay, so that's kinetic energy. We'll do some example problems in just a minute. All right, and so then we're going to potential energy. Upstaged by the bell. All right, potential energy. So this is the energy of position. So this is the energy of position. Okay, and the symbol that we use for this is, there's two symbols. We like to use the general symbol U, like a capital U. That doesn't look like a capital U, but it's capital U. And the unit is still a joule. Energy is in joules. Now there's two different types of potential energy. Okay, so we have to deal with that. They have different different symbols and different formulas. So gravitational potential energy, in order for something to have gravitational potential energy, an object must be off the ground. So it can't be sitting on the ground to have gravitational potential energy. Okay, the symbol for that is U with a subscript of G for gravitational. And the formula, so UG is equal to mgh. So that's M for mass, G for gravity, and H for height. Now height needs to be in meters, okay, because that's the SI unit for length is meters. Okay, the other type of potential energy is called elastic potential energy, and this is when an object is stretched or compressed. Okay, so what kind of objects would stretch or compress? That could be a spring, could be like a rubber band, like things that are stretchy. So if you think of things that are stretchy, they have elastic potential energy. Now they only have this elastic potential energy when they're stretched or when they're squished. Okay, otherwise they don't have the elastic potential energy stored. They're just relaxed. They don't have any energy. Okay, they have to be stretched or compressed. And so the symbol for that is U with a lower subscript of E. So UE for elastic potential energy. And UE is equal to kx squared over 2, or some people like to say 1/2 kx squared. Okay, and this one is weird. This is where k is the spring constant, and x is how much that spring or whatever stretchy is compressed or stretched. So those are weird things, okay? So k, we call that the spring constant. And the x, it has to be in meters. This is the amount of stretch or compression. And it has to be in meters. Can you see that? Yeah, you can still see that. Okay, you have to do x in meters. A lot of times they like to give it to you in problems in centimeters, and you have to convert it to meters. So you need to remember that there's 100 centimeters in a meter. So if they give you centimeters, you need to move the decimal or the imaginary decimal place over 2 places to the right, or multiply it by 100. I said that wrong. 2 places to the left, or multiply or divide by 100. I said that wrong. Yes? K is the spring constant. K is the spring constant. Okay. Hooke's law is what you would use to find the spring constant in cases where you don't actually know the energy. Okay, so Hooke's law is kind of, it's a formula. So Hooke's law, let's see, you actually have, all of this is on your formula sheet. So if you look at your formula sheet, we have work, the energy for work, or I'm sorry, the equation for work is there, and there, there's work at an angle, and then power, and then there's UG, gravitational potential energy, the formula is right there, okay? Elastic potential energy, it's right there. Kinetic energy is right there. And then there is Hooke's law. Hooke's law is K equals F over X. Okay, so all of that is right there. So Hooke's law, K equals F over X, where F is the force to stretch or compress, and X is the, you know what that is, that's the amount of stretch or compression. Okay, so we like to use Hooke's law to find the spring constant if we don't have the energy stored in the spring. Okay? I don't really have anything for other forms of kinetic and potential energy, so we're just going to kind of, no, don't worry about that. So that's everything you need to know about energy. Okay? Now we're going to do a few example problems real quick. All right, so in this example problem, kinetic energy example problem, Joey is running 17.052 meters in 5 seconds. That's that hill outside. Joey's really fast. If Joey's mass is 65.5 kilograms, what is his kinetic energy? Well, KE equals mv squared over 2. I have his mass. This is his mass. I don't have his velocity. So first I have to calculate his velocity. Okay? Well, velocity is just displacement over time. I have displacement, and I also have time. So I can plug that in right quick and get that. So I have 17.052 meters over 5 seconds. Okay. So I get about 3.4 meters per second is good. So when I'm going to plug that into my KE equation, right? So his mass is 65.5 times his velocity, which is 3.4, squared. Don't forget the square. People forget the square, and that's a problem. Don't forget the square. Over 2. Now, a square and an over 2 don't cancel. Please don't, assume that they do, okay? So we have 65.5 times 3.4 squared over 2. All right, and so you get about 370, I'm just going to go with 379. So 379, and because this is energy, it's measured in joules. So 379 joules of kinetic energy. Okay, so for potential energy, remember there's two different types. Okay, there's one where something has to be off the ground, and there's one where something in the problem is stretchy. Okay, so first example problem, a 20 kilogram box is lifted 8 meters, calculate the potential energy. So is this off the ground or is it stretchy? Off the ground. Okay, so if it's off the ground, we're going to use UG, gravitational potential, okay, which is equal to mgh, where m is the mass. Well, they gave us the mass, 20 kilograms is the mass. We know g is 9.81, and they gave us the displacement, the height, right? So there we go. So then you just plug that in. So 20 times 9.81 times 8. You can't really see that very well, but it's 1570. Okay, so about 1570. So 1570, and then what is energy measured in? Joules. Okay, so here we have a spring system with a before and an after. So before it's relaxed, afterwards I've hung a 10 kilogram mass from it, and it's hanging vertically. So the only thing acting on the mass is gravity. Okay, and then I put a ruler next to like where it started to where it stretched to. So from there to there, that's how far it stretched. Okay, so I want you to, from this picture, calculate the spring constant and the potential energy. Okay, well, to calculate the spring constant, I'm going to have to use Hooke's law. So Hooke's law is K equals F over X. Now, F, in this case, because it's hanging vertically, my F is attributed to gravity. So what F am I going to use? FG. Yeah, so I'm going to use FG right here. I'm going to use FG. Okay? So FG is just mg, right? So I'm going to modify this equation a little and call it mg over x. Okay, I have the mass. This is the mass. And then according to my little scale here, what is my x equal to? How many centimeters? Probably about 5, right? So 5 centimeters. Remember I said it was a centimeter ruler. All right, so then this is my x value, this is my m value, and then I know gravity. So it would be 10 times 9.81 over, is 5 acceptable to put there? How many meters is 5 centimeters? How many? 0.05. Yeah, so you 0.05. So you divide it by 100 to find the number of meters. All right, and then we just plug that in our calculator. All right, so 10 times 9.81 divided by 0.05. And I get 1962. And, oh, I forgot to tell you the units for spring, because F is measured in newtons and X is measured in meters, this is a newton per meter. Like, that's literally the unit you use. It doesn't have something special like a joule. And then part B, we want, well, okay, so it is a spring, so which type of potential energy are we going to use? The UE, because it's elastic, okay, it's stretchy. So we're going to calculate UE. UE is kx squared over 2. Well, now we have k, so we just plug that in. We figured out our x, but in meters it's 0.05. Don't forget to square it, because if it's squared in the equation, you must square it in real life, divided by 2. Okay, so then we stick that in our calculator. Okay, and so you get 2.45. Okay, so 2.45, and then the unit for energy is a joule. So 2.45 joules. Okay, the work energy theorem is another equation. It's in your formulas. Okay, so it's right here. Work equals delta KE, which equals that. Okay, so this is what we're doing now. Okay, so we're going to copy that down under work energy theorem. Okay, so work energy theorem, work equals delta KE. What does that mean? Work is if work is done, I'm not going to make you do work at an angle for the work energy theorem most of the time because that's kind of rough. But if I plugged in the formula for work, work is force times displacement, and delta KE means a change in kinetic energy. So the only way you can change your kinetic energy, okay, if it's dependent on mass and it's dependent on velocity, if you're riding in a car, can you suddenly change your mass to change your kinetic energy? No. I mean, you can't like rip seats out of the car and like throw them out of the car and change the mass of the car. That's not going to work, okay? I guess you could if you were the Hulk, but you're not. So what you can do is speed up or slow down so you can change your velocity. So when you change your KE, your mass will typically be the same unless you're the Hulk and you can throw things. But your velocity will change. So it will be V final squared minus V initial squared over 2. Okay? So this and this are the same thing. Okay, it's called the work energy theorem. So work is done if something changes direction or changes speed. It has to be accelerating in order for this work energy theorem to apply. Okay? So we're going to do a little example problem. In your homework packet, we're going to do, let's see, I'm going to do number 15 for you, so I'll take some of your homework away from you. So we'll do number 15 together. So let me read number 15. So because your homework tonight is page 26 through 27 and all that, right? Okay, so I'm going to do number 15. I'll do the first one for you. All right, so page 27, number 15. All right, so it says on that page you have, on the wrong page. There we go. It says, no, that's too easy. Number 24. We're going to do number 24 for you. 24. Page 27, number 24. Sorry about that. All right. All right. You have a 5 Newton horizontal force hits a stationary 2 kilogram ball. And if it's stationary, how fast is it going? 0. So its initial is 0. Okay. And it says, what is its speed after going 10 meters? Okay, so they're telling you some information in this problem. It might be helpful to jot it down, but they're telling you the force is 5 newtons, and the mass is 2 kilograms. Can you see this? Okay. Let's see. Where am I? Here I am. Okay. And it's stationary to begin with. That means your V initial is 0 meters per second. And you're looking for how fast it's going at the end. That's V final. So you're looking for V final after it has gone 10 meters. So your displacement is 10 meters. Okay? So you're going to use this equation, right? So you're going to do F times S equals M V final squared minus V initial squared over 2. Okay, so I wouldn't do a ton of algebra with this. I would probably just go ahead and plug and then do the algebra with the numbers, okay? But if your VI is 0, you can probably just get rid of it in your equation and then plug everything else in. So your F is 5. Your S is 2. Your mass is 2. your V final is what you're looking for, but it's still squared, okay, over 2, because 2 is in the equation. So look at that. 2 over 2 equals 1, right? It cancels. So those 2 will cancel. And then if you're looking for just V final, what do you do to the whole other side? Square root. So you square root to get rid of that square. So V final is equal to the square root of 5 times 2. Okay? That's 10, by the way. So the square root of 10 is 3.16. Yes, it should be. It should be 10. Right there. You're right. And I am wrong. 5 to the square root of 50. My bad. I can read. Reading's hard, but I can do it. All right. 7.07 meters per second. Bye. See you Friday.